And so let me introduce the next speaker of today, Alexandr Zubkov from United Arab Emirates University, and he will talk about separating vector invariants of group G2. Please.
Okay. So first of all, my thanks to organizers of this, how to say it, conference or workshop, and also my special thanks to anybody who is still here in this audience, because of course I understand that it is quite long that we are sitting here. Again, so I'm going to talk about the separating invariants. I will explain later what does mean this word vector. So I have some strange cursor here. I will change it. I don't know. Okay, so I'm going to talk about invariants of the well-known simple exceptional group of type G2. We'll use this scrolling. And because of the main hero of my talk is not associative algebra, so first of all I have to remind you some definitions here. Again, as in many previous talks, I will start with the infinite field K of arbitrary characteristic. Mainly, it will be just algebraically closed field, but it's just a nude condition. So, and I will just introduce, I will just remind the definition of the algebra of octonions, or in a split form or Zorn form. So this is a split Kelly algebra consisting of all matrices of this form. So what we have here, this is a 2 times 2 matrix. Okay. On the main diagonal we have scalars from our ground field K, and these elements U and V, they are just vectors from 3-dimensional vector space. And we can define, on the set of these matrices, we can define non-associative product by the following formula. So if we have 2 octonions, A and A prime, so A has already appeared here, A prime has the same form. All you need just to put primes everywhere. And in this product, you see that in this product, the dot product between vectors and cross product between vectors, they are involved. So this is the definition of the product in algebra of octonions. Okay. And this product, as I said, this product is non-associative, but this algebra, it is well known, it is a simple alternative algebra. The term alternative means that any couple of octonions satisfy an associativity law. Okay, and also this algebra of octonions has some sort of analysis of trace of matrices and determinant. So what they are. First of all, we can define on this algebra of octonions the linear involution by the following formula. So A will be can be mapped to A bar. So what we are doing here, just to remind you, is that A has coordinates, entries alpha, beta, u, v, alpha, beta scalars. So what we are going to do here, we are going to flip these entries on the main diagonal, and the entries in this, how to say, quasi-diagonal, so it will be just negatives of the previous entries u and v. Okay, it is clear that the sum of A and A bar, it is just scalar matrix with the same entries in the main diagonal. So I'm going to identify such matrices with the scalars from the field. And also we can define the norm N of A. So this I'm going to denote by T of A with a trace. And the norm N of A is just the product A bar. It is again some scalar or scalar matrix. Okay, and this function norm is a multiplicative function. So the norm of product is a product of norms of the factors. And also we have a sort of Kelly-Hamilton identity here as for 2 by 2 matrices. So it is written as this identity has a standard form. So A squared minus trace of A times A plus norm of A equals 0. Okay. Well, the next hero of my talk is the group G2. So, okay, now I'm going to assume that the ground field K is algebraically closed. Then you can consider the automorphism group of this algebra. And it is well known that this automorphism group is isomorphic to the first exceptional simple group of type G2. In what follows, I'm going to denote this group by the same symbol, G2. Okay. So this is the incarnation of this group G2 as the automorphism group of octonions. Probably, for the best of my knowledge, it was probably first discovered by Eli Cartan more than 100 years ago, so in 1908. Okay. And now I'm going to define what kind of invariants we are going to study here. So, okay, so let me say a few words about the octonion algebra as a representation of this group G2. The octonion algebra has dimension 8, and in some sense it is a minimal or standard representation of this group G2. Minimal, by the word minimal, I mean that this octonion algebra is a model it is really a simple model of the minimal fundamental weight for the group G2. It is the same sort of representation as a standard representation of general linear group. Okay, and because of this, of course, it would be quite interesting to describe the invariance of the diagonal action of group G2 on several copies of the algebra of octonions. It exactly corresponds to the case of vector invariance of general linear group. This is why I'm going to call this invariance like a vector invariance. Okay, so as in many previous examples which were given in the previous talks, I'm going to define the algebra of invariance. So I consider the space of n copies of octonions on which our group G2 acts, of course, diagonally. Okay, and this action of G2 on several copies of octonions induces the standard action on the coordinate algebra of this vector space of several copies of octonions, and the invariance of this action, they will be called like a vector invariance of octonions. The typical examples of such invariants are just norm function and trace function of the product of octonions. But here I have to emphasize that I mean that this product of octonions has a, I mean, you can put the brackets in these products in many different ways because of our algebra is not associated, right? So here for this product of several octonions, I mean that I can consider this product in many different ways. So the result is not uniquely defined here. So for all possible arrangements of brackets here, you can define many different traced functions. Okay. In what follows, I'm going to omit these brackets. Okay. Oh, by the way, some simple remark. The norm, of course, if a characteristic of the ground field is not 2, then the norm can be defined by the standard formula for the determinant of 2 times 2 matrices, or 2 by 2 matrices. Sorry. Okay. Now, these invariants, the vector invariants of several copies of octonions, they were first described by the Schwarz in the 80s of the previous century, and later in our joint work with Professor Ivan Shestakov, we just extended the result for the case when characteristic of the ground field is positive but not equal to 2. And we have proved that really it's interesting, but the set of generators of this invariant algebra for the case of positive characteristic is exactly the same as the set of generators in a characteristic 0. And the result is as follows. This algebra of invariance is generated by the trace function. Okay, the proof is really very technical, and I used, for example, the theory of models with good filtration, and the Fenov theorem due Donkin and Mathieu. And also another very deep result by Rybnikov and Adamovich. Okay, it's a different story. I'm not going to some details here. Well, but we still have the same question for the case when characteristic of the ground field is just 2. In this case, the set of generators of this algebra is not known yet. And the previous approach, I mean, the previous approach by me and Professor Shestakov cannot be realized here because of our approach was based on one of some fundamental observations that, for example, if you will consider a representation of the group G2 on exterior powers of the minimal representation, I mean, on the algebra of octonions, all these models, they have good filtration. But in a case of characteristic 2, so some of these exterior powers, they do not have good filtrations. And our previous approach cannot be performed here. It's not possible just to just to repeat the main steps of this approach. This is why with Artem Lopatin we decided just to how to say to formulate and to formulate the weaker form of the first fundamental theory for several octonions. So we decided to calculate the separating invariance of octonions, and here we obtained the following results. First one is as follows. If characteristic of the ground field is not 2, then the algebra of vector invariants, octonions, has a minimal set of, I'm going in the wrong direction. First of all, we formulated the following improvement of the theorem by me and Shestakov. So first of all, we have already proved, we proved that if the characteristic of the ground field is not 2, then the invariant algebra of octonions has a minimal set of generators consisting of all trace functions of degree at most 4. Okay? And also we assume that arrangement of brackets is given from the left to the right. Okay? So it is a really minimal set of generators. So any subset of this set is not generating this algebra of invariants. And next, okay, I think that it doesn't make sense now to remind the definition of separating invariants because it was done in a talk by Jonathan Elmer. Okay, but I will say a few words maybe about the equivalent definition of separating invariants, which was also implicitly mentioned in a talk by Jonathan. But okay, let me just say a few words about it. The original definition is equivalent to the following. So the set of invariants, say this capital S, the set of invariants, is a set of separating invariants. If these separating invariants separating closed orbits. So it means that if you have two different closed orbits of n tuples of octonions, then they can be separated. So you can find some polynomial from this set S, right? For which the value of this polynomial invariant on a one tuple n tuple of octonions is different from the value of the same invariant polynomial on another tuple n tuple of octonions. Okay. In the case when these n tuples generate the orbits of these n tuples are closed and different from each to other. Okay. Now I can formulate the main result of our work with Artem Lopatin. Okay, as you see, the previous result was given. I mean, both results, Schwarz, Zubkov, Shestakov result and Lopatin, Zubkov result. For both results, we know the minimal set of generators in a case of characteristic of ground field not equal to 2. Okay. Now we can formulate the main result for the ground field of arbitrary characteristic. Okay. So in this case, so we proved that the algebra of it is a type of field. Of course, it should be the algebra of invariants, not coordinate algebra of tuples of octonions. Okay, so the algebra of invariants of octonions has a set of separating invariants consisting of traced functions of degree at most 8. So as you remember, in the case of odd characteristic of the ground field, this algebra is generated by the trace functions of degree at most 4. But if you go further to the characteristic 2, so this result should be a little bit changed. So we have to admit the degree at most 8. And again, with arrangement of brackets from the left to the right. Okay. Now I will say a few words about the proof of this theorem. First of all, the proof of the theorem can be reduced to the following statement. So the proof is based on the following crucial statements. So the set of polynomial invariants of degree at most n is separating. I'm talking about the vector invariants of octonions, of course. So the set of polynomials of degree at most n is separating if and only if this set separates the closed orbits of very specific form. So we have two orbits here. This A, this underline. How to say? I don't remember this English term. Okay, maybe under bar. And this orbit. Assume that they are closed orbits. Okay. And also assume that the first n tuple has the following form. So some of these coordinates they can be 0 octonions. Right? Okay. And here the another n tuple just in some sense. Okay, I'm not going to assume that here some of the coordinates are 0. And what we can what we have to assume here that A1, AL, these first coordinates here, they form a basis of some subalgebra of algebra of octonions. And B1, Bn, they just span some subalgebra. Now let me denote first subalgebra by A and second subalgebra by B. And also the dimension of first subalgebra A is at least dimension of the second subalgebra B. Okay, from here it's clear that immediately that this number L cannot be bigger than the dimension of the algebra of octonions. So L is at most 8. Okay, I cannot say anything about the subalgebra B, but I assume that the dimension of B is at most dimension of the subalgebra A. So what does it mean? It means that we have to consider the couples of closed orbits of very specific form. Okay, the first orbit is generated by the L tuple of octonions, and this L tuple is just the basis of some subalgebra. And another point, I mean that another n tuple of octonions for the second closed orbit also span some subalgebra. So really, we are working with the subalgebras in the algebra of octonions. And of course, we have to describe all possible types of subalgebras in algebra of octonions. But this question can be reduced to the question about the maximal subalgebras of algebra of octonions. But the maximal subalgebras, I mean maximal proper subalgebras of algebra of octonions, they have already been described in the long known, I mean in some article by Racine. The answer is, okay, I'm not going to to describe it here, but the answer is as follows. The maximal subalgebra of algebra of octonions has a dimension at most 6, and the subalgebra of dimension exactly 6 up to the action of our group G2 can be described, I mean that the basis of this subalgebra can be described explicitly. And what is interesting here, so if you will take this subalgebra of dimension 6, then using the if part of well-known Hilbert-Markov criteria, we can just show that the orbit of the corresponding 6 tuple is not closed. What does it mean? Let me just remind you something about this Hilbert-Markov criteria. So we can consider one parameter subgroups of the group G2. So the one parameter subgroup is just image of one-dimensional torus. Okay, and you can consider the action. For example, you are given by the closed. You are given by some orbit. Okay, of n tuple of octonions. So you can define the action of this one parameter subgroup on this orbit. Okay, then it's clear that because of this one-dimensional torus, your orbit will be expressed as a sum, in some sense. It will be expressed as a sum of weighted components, right? Each component corresponds to some power of the parameter. Okay, and if you have, it assumes that in this decomposition, in this expression, all degrees of the parameter t, they are non-negative. Okay, even I assume that all of them they are positive. In this case, your orbit contains the 0 point, but if you have some component whose weight is exactly 0, you can just drop down the rest sums in the weighted decomposition, and you can leave only the component which corresponds to the weight 0, and this component belongs to the Zariski closure of your orbit. So using this trick, you can simplify in some sense the original n tuple of octonions. Like in this case, if you will consider the basis of this 6-dimensional subalgebra of algebra of octonions, you can show you that this the corresponding orbit of these 6 elements with respect to the action of the group G2 contains subalgebra of dimension 4. Okay, you see that we have just sort of nice reduction. You start with the dimension 6, and you can reduce it to the dimension 4. In the case of dimension 4, you have to consider subalgebras which have a basis of 4 elements. And using another combinatorial arguments, you can reduce even this case to the case of the subalgebra for smaller dimension, up to 3. Right? And when you will get it, using some in this case, again, you can, okay, this case can be just split it in 2 subcases. And really, the case of the subalgebra of dimension 3 also can be managed. I'm not going to some details here, but this way or another, using this trick with Hilbert-Manford criterion and also another combinatorial arguments, we can just reduce the general case to the case of couple of octonions. And in this case, we can just completely classify these couples of octonions, which has been done in another article by Artem Lopatin and me. Okay. And in the last case, when we are working with only couple of octonions, it is just sort of case-by-case verification of our statement about separating invariants. Okay, so more or less these are main steps, and there's some outline of our proof. Okay, here I just will show you the references. Okay, this article by Racing, which appeared in Journal of Algebra. Okay, more than it's about 50 years ago. It's a very old result. So our work with Artem Lopatin, they are available at arXiv. Okay, and now there is a chance that this article about separating G2 invariants of several octonions will appear in a journal of algebra number theory. I hope that it will be available very soon. Okay, this is our article with Shestakov. Well, I think I have some time. Let me finish with sort of perspectives here. So what we are going to do later? Now we are working on the same kind of problem, but for the next exceptional simple group of type F4. This group can also be defined as an automorphism group of some non-associative algebra. It is a well-known Albert algebra, which is 27-dimensional. These are so-called Jordan algebra. And what's interesting, this is a commutative algebra, but non-associative algebra. So we are going to apply the same approach here. But of course, this case is much more complicated because of the structure. Even this idea about maximal subalgebras, probably it can be realized, but the complete description of maximal subalgebras in Albert algebra is much more complicated. And so far, we are at the very beginning of this project. Okay, I think because of it is a last talk today, I was not going to take a lot of your time. So let me just finish here. So thank you for your attention. I'm done.
Thanks a lot for your detailed talk. Are there any questions or comments? Well, okay, then I will ask. And of course, I know what we are doing with you right now, but so my question will be about these methods to find out generators for some exceptional groups using good filtrations. So is there any chance to apply it for, I know, F4 or E6, let's say?
Yeah, it's possible, but for the sufficiently big characteristic, the problem is the same as the case. I mean that the issue is the same as in a characteristic proof for the invariance of octonions. Because of again we have the same. We have the same phenomena because of the exterior powers of this minimal representation for the group F4. Unfortunately, they do not have good filtrations if the characteristic is small. What I mean by this, for the group F4, I can prove that exterior powers of the Albert algebra, they have good filtrations only if the characteristic is at least 13. Oh, sorry, no, at least 17. So if characteristic is quite big, quite large, we can mimic. We can just repeat the same approach. But if characteristic is less than 17, I don't know. So I can prove that the exterior powers do not have good filtration. And this is a problem. So we cannot realize the same approach as in my article with Ivan Shestakov. Unfortunately, it's not possible. But what is the really? Let me just say a few words. What is the advantage of this of the existence of these good filtrations? If you can prove that all exterior powers of the minimal representations they have good filtration, then you can prove very nice result. This result says that you can obtain the set of generators from the multilinear generators. From multilinear invariants. What I mean by this, if you can describe the multilinear invariance of the action of your group, that of course, okay, assume that you have invariant of degree n. If it is multilinear, it means that this invariant depends on n, how to say it, on n general octonions, okay, or n general, how to say it, general. So really, I have to explore some term here because
Albertanians, I don't know.
Albertanians, or something like this, Albertanians, because they are elements of Albert algebra. Okay, say Albertanians. So, and okay, you have this invariant, which depends on degree n, which depends on n Albertanians. And what you can do now, you can just specialize some of these Albertanians to the same one, right? So it seems that you have f, x1, x2, x3. Now you can specialize x1, x2 to the same x, right? So you will get non-multilinear in there. And of course you can specialize these three Albertanians to the same one. So you will get another invariant which is not multilinear, right? So if you do it with any multilinear invariance, you will get exactly the set of generators of your invariant. This is the advantage of this result. So if you will prove that any exterior power has a good filtration, it has a very good consequence. All you need is just to describe multilinear invariance. But the main idea of this proof is not polarization. The technique of polarization doesn't work here. It doesn't make sense because we are working in a positive characteristic. And the reason why I can use multilinear invariance is absolutely different. It depends on this very deep theory of models with good filtration. Okay, I think it's enough.
Okay. Thanks a lot for your reply. Any other questions or comments? Okay, then let's thank the speaker again. And I would also like to thank all speakers of today for their talks. Okay. And so see you all tomorrow during the second day of our workshop.